Have you ever wondered how pharmaceutical scientists ensure that a drug remains safe, stable, and effective throughout its entire shelf life? Behind every approved medicine lies a rigorous experiment, the Forced Degradation Study, or FDS, a cornerstone defined by the ICH Q1AR2 guideline. At ResolveMass Laboratories, we conduct these studies not merely to tick a regulatory box, but to truly understand how molecules behave when they're pushed to their limits. Forced degradation isn't just about destroying a drug, it's about understanding it. By intentionally exposing a compound to extreme conditions like acid, base, oxidation and heat, we uncover how and why it degrades. This tells us three vital things. First, where the molecule is chemically weak, those ester or amide bonds that break down under stress. Second, what degradation pathways exist, the chain of reactions that lead to new chemical entities. And third, what byproducts are formed, information that becomes the foundation for analytical method development. Every forced degradation study tells a story. The story of a molecule's resilience and the analytical scientist's ability to quantify it. The ICH Q1AR2 guideline sets a clear standard for how we perform forced degradation studies. It requires testing under all major stress conditions: acid, base, oxidation, thermal, photolytic, and humidity. But it's not just about exposure, it's about control. The degradation should fall between 5 and 20%, enough to reveal chemical weaknesses without over-destroying the molecule. And documentation matters. Every pH, every solvent, every hour of exposure must be recorded with precision. Finally, the method must be stability indicating, capable of distinguishing the pure drug from every degradation peak. Meeting these expectations ensures regulatory compliance and scientific credibility. The 5 to 20% window is more than a regulatory recommendation, it's a scientific balance point. If degradation is below 5%, you might not see enough change to understand the molecule's vulnerabilities, but push beyond 20% and you risk creating degradation artifacts that would never appear under real-world conditions. That's why we use tools like design of experiments, DOE, to fine-tune parameters like temperature, reagent concentration and time until we hit that sweet spot. This range produces just the right amount of stress, enough to challenge our analytical methods while keeping the degradation meaningful and reproducible. Let's start with the first two major stressors, acid-base and oxidation. In acidic or basic hydrolysis, we test how the molecule reacts in extreme pH conditions, simulating environments like gastric acid or basic cleaning solutions. This helps us identify which functional groups, like esters or amides, are most sensitive to pH shifts. Next is oxidative stress, often induced using hydrogen peroxide. It mimics oxygen exposure, crucial for products stored in air-permeable packaging. Through these studies, we not only map out chemical vulnerabilities, but also design better formulations and packaging to counter them. Now we complete the picture with thermal, humidity, and photolytic stress. Thermal stress tests how the molecule and excipients hold up at elevated temperatures, critical for defining storage and shipping conditions. Humidity studies measure how moisture affects both physical and chemical stability, especially for hygroscopic or amorphous compounds. And photolytic testing exposes samples to UV and visible light as per ICH Q1B, revealing whether light can trigger degradation. Together, these stress studies create a complete stability fingerprint, helping scientists design formulations that stay stable under every possible challenge. In reality, things aren't always clean. Excipients in formulations can degrade too, and their byproducts sometimes overlap with the API peaks. To resolve this, we conduct placebo stress testing, applying identical stress conditions to the formulation without the API. By comparing chromatograms of the stressed product and placebo, we can identify which peaks belong to excipients and which belong to the API degradation. This approach satisfies ICH Q1's requirement for specificity and ensures that our methods are robust, reliable, and interference-free. One hallmark of a well-executed forced degradation study is mass balance, the idea that what's lost as API must appear as degradation products. Ideally, the sum equals 97 to 104%. If it doesn't, something's missing. Maybe a volatile impurity, a non-UV active degradant, or an incorrect detector response. That's where relative response factors, RRFs, come in. They correct for differences in detector sensitivity between the API and each degradant. By applying RRFs, we achieve quantitative completeness, ensuring our analytical picture truly reflects chemical reality. Once degradation products are identified, we move to LC-MS/MS, the detective of analytical chemistry. Here, each molecule is ionized, fragmented, and analyzed based on its mass-to-charge ratio. These fragments create a unique fingerprint that allows us to determine the exact structure of each degradation product. This process reveals the mechanism of degradation, whether it's oxidation, hydrolysis, or rearrangement, giving us molecular-level insight that feeds back into formulation design and impurity control strategies. When we map degradation pathways, we're connecting environmental stress to molecular change. This map informs every downstream decision, from choosing excipients that stabilize rather than react, to selecting packaging that protects against light or oxygen. It even defines appropriate storage conditions, ensuring that the product's shelf life reflects real-world stability. In short, degradation mapping transforms raw analytical data into actionable formulation strategy. To predict how long a product will last, we turn to kinetic modelling using the Arrhenius equation. By studying how the rate constant changes with temperature, we can calculate activation energy and extrapolate stability to room temperature. Plotting lnk against 1/T gives a straight line, the famous Arrhenius plot, allowing us to predict T90, or the time when 90% of the drug remains potent. This mathematical approach gives manufacturers early insight into shelf life, years before long-term studies are complete. At ResolveMass Laboratories, forced degradation is more than a compliance exercise. It's a tool for scientific foresight. By combining precision experimentation, LC-MS characterization, and kinetic modelling, we not only satisfy ICH guidelines, we deepen molecular understanding. Forced degradation transforms stress data into actionable knowledge, analytical confidence, and ultimately, product trust. Because in the end, stability isn't just about keeping a molecule intact. It's about ensuring every patient receives a drug that performs safely and consistently, every single time.